So this is a typical situation in which we are using or thinking of a model that is a polynomial function with fourth degree, even degree, and having 3 terms, 1, 2, 3. Any questions on this? Okay. So the next step is we're going to look at dividing polynomials, section 3.3. And we're going to look at how we divide two polynomials, a polynomial by a monomial and a polynomial by a polynomial. Okay? Just a quick review, and then we look at rational functions. So this is 3.3, division of polynomials. Division of polynomials. Oops. Okay. So when I divide a polynomial by one term, like for example x cubed, all I have to do is just separate the fraction. I will separate the fraction in several fractions depending on how many terms does the polynomial at the top has. So here's an example. I don't think there is an example in the book. This is just a quick refresh your memory for it. So I'm going to make one up. So for example, I have negative 3x to the fifth plus 4x squared minus 3x and plus 1. Now let's suppose I want to divide by x cubed. Because the denominator is just one term, the only thing I can do, and if you would say, oh, that this is not a real division, I would have to agree. It's really not a real division, but it helps for something in this chapter. So negative 3x to the fifth over x to the third plus 4x squared over x to the third minus 3x over x cubed plus 1 over x cubed. So I split the fraction into, in this case, 4 fractions, depending on the number of terms, right? It's 4 because the number of terms of a polynomial from the top is 4. Now, what do you think I'm going to do with each individual fraction? I'm going to simplify, right? So I'm going to simplify x to the fifth and x to the third, removing 3 of these. So this is negative 3x squared. I'm going to simplify removing 2 and 2, so it's plus 4 over x, minus, I'm going to remove 1 from each, so it's minus 3 over x squared plus 1 over x cubed. That's all I can do. So when the denominator is just one term, that's my only chance. Now when we divide a polynomial by a polynomial, so p of x divided by another polynomial, we have 2 options. One option works always, which is long division. The other option works only when q, the denominator q of x, the denominator, the polynomial in the denominator is, no problem, only if the polynomial in the denominator is a binomial, preferably with a leading coefficient of 1 and degree 1. So something like p of x divided by x minus a number. This is called synthetic division. So the synthetic division has limited applications. It's applied or can be applied only if the denominator looks like this. If the denominator is x squared minus 5, we cannot apply synthetic division. So let's start by looking at a couple of examples. You know what I forgot, right? let's look at a couple of examples with long division and then with synthetic division. On page 392, let's start with 13. This is review from previous course. However, I would like to refresh your memory on this because there is homework on this, so that's why. 3x squared minus x minus 3. Okay. First question here that I ask myself is, are these two in descending order? Because if they are not in descending order, I have to put them in descending order. Are they in descending order? Perfect. So let's start the algorithm. Is there any missing term from the top? What is the degree of the top? Good. Degree 3 is there, degree 2 is there, degree 1 is there, degree 0 is there. No missing terms, so I do not have to leave any empty space. 6x cubed plus 13x squared minus 11x minus 15 divided by 3x squared minus x minus 3. First question, 3x squared multiplied by what is 6x cubed? So 3x squared multiplied by what is 6x cubed? Indeed. We will distribute 2x to 3 terms. 1, 2, 3. Write the resulting terms under the like terms, but not before we change to the opposite sign because we have to subtract. Okay, let's do this together. 2x times 3x squared. Very good, but I have to subtract. I have to change the sign before I write. 2x times negative x plus 2x squared, and I have to write under the like term. 2x times negative 3 yes, so it's negative 6x, but I have to write plus 6x. I perform the operations I see. Gone. 15x squared minus 5x, and I bring down the next in line. Final question. 3x squared multiplied by what is 15x squared? Here I cannot lie. The question, I have to write the exact sign. When I distribute and I write underneath, I have to change to the opposite sign. So 3x squared multiplied 3x squared multiplied by what is 15x squared? Sign. Yes, the top is the true sign. 5 times 3x squared is 15x squared, but we have to subtract. 5 times negative x is negative 5x, but I have to subtract. And 5 times negative 3 is negative 15, but I have to change the sign. It happens that there is no remainder. If it were a remainder, I would have written the answer as quotient plus remainder over the divisor. But since the remainder is 0, I only have a quotient. What is the quotient? 2x plus 5. Any questions on the long division? Any questions on the long division? Do you think we need another example?
What would you write the remainder if you had one?
So for example, let's say the remainder is 5. I would write the answer as 2x plus 5 divided by 3x squared minus x minus 3. if the remainder were whatever.
Yeah.
It can be something with x in it. True, it's possible. So I will write whatever I get. If I get negative, then I will put negative in front. Okay? Do we need another example, or can we refresh our memory on the synthetic division now? Are we okay with this? Okay, so let's take a look at synthetic division. Here's an example. Feel free to choose if you want. I'm going to choose 22 on the same page, 392. And we have 5x cubed minus 6x squared plus 3x plus 11, and everything divided by x minus 2. Question: is the top in descending order?
Yes.
Any missing terms? It's based on the degree. What is the degree of the top? It's 3. So degree 3 is there, degree 2 is there, degree 1 is there, degree 0 is there, no missing degree. No missing term, if you want. Okay? The synthetic division has a little box, if you want. In this little box, we have to put this number. If the divisor, which is in this case x minus 2, if the divisor is x plus 5, what do I have to put in the box? Negative 5. If I have x minus 2, I put 2. So the synthetic division is applicable only when the denominator is x minus a number, but I have to identify that number. If I have x plus 2, a is negative 2. If I have x minus 7, a is 7. Good. So in this case, we have 2. The next step, I will copy all the coefficients. If there is a missing term, then I will copy 0 for that missing term. But there are no missing terms here. So 5, negative 6, 3, and 11. I will leave some room under these numbers and then draw a horizontal line. Synthetic division requires that the first digit, which is the leading coefficient of the numerator, of the polynomial in the numerator, must be copied. We don't do anything to the first coefficient or the leading coefficient. Here's the next step. We multiply 2 by 5. 2 times 5, and we write the answer here. We perform the operations we see as negative 6 plus 10, which is 4. We continue multiplying now 2 by 4, and we get 8. We perform the operations we see. 3 plus 8 is? And now the last step is 2 multiplied by 11, which is 22. So the remainder, and the remainder has to be boxed in. The remainder in this case would be, that's it. Now, how do I know how to write the answer? Very, very easy. Again, what is the degree of the numerator? And what is the degree of the denominator? Degree 0 is for a number. So this is a linear function, degree 1, correct? Okay, so when I divide degree 3 by degree 1 in general, what degree do I get? 2. So this is the coefficient of what term? You already told me. When I divide degree 3 by degree 1, I get degree 2. So this is the coefficient of x to which power? X squared. This is the coefficient of x to the first power, and this is the free term. So that's how you identify what this represents. So can anyone tell us the answer, the final answer? How do I write the final answer of this division?
5x squared
Perfect.
plus 4x
Perfect.
plus 11 divided 33
Say it again.
and plus 33 remainder
33.
over x minus 2.
That's it. How do I check this answer? What if it's wrong? Let's say I want to check. How will I check? I will multiply all this by x minus 2 and add 33. When I multiply all this by x minus 2 and add 33, what should I get? Can you dictate? Can you read? When I multiply this by x minus 2 and add 33, what should I get? The numerator. 5x cubed minus 6x squared plus 3x plus 11. If I don't, this is wrong. Do we need to check? How do I check that 10 divided by 3 is 3 integers and 1/3? 3 times 3 plus 1, and I get 10. So if this times this plus 33 does not equal this, all the calculations here are wrong. I mean, this is not the correct answer. Do we need to check? Yes, okay. I got one yes, so let's do it. So I will multiply 5x squared plus 4x plus 11 multiplied by x minus 2 plus 33 and see if I get this. If I get this, the answer is correct. If I don't get this, the answer is not correct. Ready? I will distribute from this small one. That's my habit. X to these three. 5x cubed plus 4x squared plus 11x, and then my negative 10x squared, negative 8x, negative 22 plus 33. This one. 5x squared, I'm sorry, 5x cubed, yes. These two, yes. Minus 6x squared. These two plus 3x, yes. And these two plus 11. So I got this back. Therefore, this is the correct division. This is the quotient, the remainder, the divisor. Any questions? Do we need another example with synthetic division? Perfect. So let's choose another. Let's say 28. I'll copy it and then I'll put my 10 copy in a second. So x to the 7th plus x to the 5th minus 10x cubed plus 12, everything divided by x plus 2. I have a few questions that I need to ask myself, and here's the first one. Top and bottom in descending order? Perfect. That's the first question. Second question, can I use synthetic division? Yes. What is the little a that goes in the box in this case? Perfect. Is there any missing term from the top? Yes. What is the degree?
7.
So degree 7 is there, but degree 6 is not. Degree 5 is there, but 4 is not. Degree 3 is there, 2 is not, 1 is not, and 0 is. Degree 0. So 1. Then for degree 6, I have to write, since it's missing, what do I write?
0.
Then degree 5,
1.
then degree 4,
0.
then degree 3.
10.
Numbers are taken with a sign, yes.
0.
0.
Plus 12.
So degree 2, degree 3, degree 2, degree 1, and degree 0. Release some room, and let's start. What is the first step? We copy the leading coefficient without doing anything to it. Perfect. Now I multiply negative 2 by 1, and I write it under the next coefficient. How much is 0 minus 2? Perfect. Now I have negative 2 times negative 2. I get, perform the operations I see. 1 plus 4 is? Negative 2 times 5. 0 minus 10. Negative 2 times negative 10. Negative 10 plus 20. Negative 2 times 10. 0 minus 20. Negative 2 times negative 20. 0 plus 40. And negative 2 times 40. And we box in negative. Perfect. Now I have to figure out the answer. What is the degree of the answer? And then I have no difficulties beyond that. So we divided what degree? By degree 1. So the first one must belong to? Excellent. So this is x to the 6th. Then minus 2x to the 5th. Awesome. Then x to the 4th minus 10 plus 10 minus 20 plus minus over x plus 2. Very good. This is it. This is the long division. Any questions? Okay, two things here that you may or may not know. Going back to our first example. Our first example had a polynomial at the top, a polynomial in the denominator, and we obtained a 0 remainder. We had no remainder, correct? So whenever I divide a polynomial by another polynomial, and I get no remainder, like for example, 9 divided by 3, is there a remainder of this division? No. Why? Because 3 is, and I'm missing one word, and then I would like you to come up with, because 3 is for 9. It's not the same thing with saying 9 divided by 5. Because 9 divided by 5 has a remainder. Because 5 is not a factor. You're on the right track. So there is no remainder here because 3 is a factor of 9. Agreed? There is a remainder here because 5 is not a factor of 9. We agree. Okay, so then what can I say about this polynomial concerning this one? Meaning, like I said here, 3 is a factor of 9 because there is no remainder. What can I say about this polynomial for this polynomial? It's a factor because there is no remainder. So the answer here is 3 plus 0 over 3. Because the remainder is 0, 3 is a factor of 9. Because the remainder of this division is 0, 3x squared minus x minus 3 is a factor of the top polynomial. We agree with that? Can I say here that x plus 2 is a factor of the top? No, because the remainder is not 0. It's negative 68. So the remainder theorem says this. If I divide p of x by x minus a, the remainder, not the quotient, just the remainder of this division of p of x over x minus a is p of a. What does this mean? It means that if I'm interested only to know whether a denominator, a polynomial, is, or just a polynomial, doesn't have to be in the denominator. If a polynomial is a factor of another polynomial, what do I have to do? As long as the polynomial looks like this. What do I have to do? Let me give you an example before you answer to that question. So x to the 4th minus 1, I don't need that parenthesis, x to the 4th minus 1 divided by x plus 1. I just want to know whether x plus 1 is a factor of x to the fourth minus 1. I'm not interested in the quotient. I don't care what the quotient is. I'm given this polynomial, x to the fourth minus 1, and I'm asked, is x plus 1 a factor of the top? I have several options. I can try to factor. I can see if I can simplify, and so on and so forth. But here's the easiest way. The numerator, let's call it p of x, which is x to the fourth minus 1. All I have to check is, what is a? If I want to use the synthetic division, what will a be? Careful, -1. All I have to check if p of -1 is 0. That's all I need to do. Because the remainder of such a division, but the divisor has to look like this, not x squared minus 15. The remainder theorem says only that if you have whatever polynomial you want at the top, but x plus 5 or x minus 3 or x plus 17 in the denominator, leading coefficient preferably 1, and power should be 1, and the power or the degree 1. Okay? Only if you have something like this, then you check p of -1. If p of -1 is 0, then you will say automatically, I know for sure that x plus 1 is a factor of x to the fourth minus 1. Is p of -1 0?
Yes.
Yes, it is. So I will say x plus 1 is a factor of x to the fourth minus 1 by the remainder theorem. Knowing that, I could also say that x to the fourth minus 1 will have x plus 1 as one factor and some other factor of what degree? I'm not asked to determine. I'm not going to determine it. But what to the degree be here? Exactly. Which can be further factorable, but I don't care. So I was just trying to illustrate the remainder theorem. Now, if the remainder is 0, as I mentioned, x plus 1 is a factor. And this is basically the factor theorem. You may encounter this in my math lab. And that's all I had to say about 3.3. We do not cover 3.4 in this class. It's a decision of my department, so I have to go along with that. So now we are ready for rational functions. Okay. We have to look at 3 different types of rational functions. How many are there? Infinite. But we can include this class, we can only look at 3 different types. Okay, so this is 3.5, rational functions. So what is a rational function? Can anyone give us an example of a rational function? Any example? We've seen them before. In what? In equations. We solved many rational equations. Just give me an example of a rational function. Awesome. Awesome. So a rational function is basically a ratio of 2 polynomials. And it happens that this is type 1 that we are going to talk about. Perfect example. Thank you. Type 2, f of x, x plus 1 divided by x squared minus 4. And type 3, f of x equals x squared minus 2x plus 1 divided by x plus 2. Okay, so now let's analyze these three types. How did I come up with these three? What's different here? So what do we notice about type 1? So both have, but they also can have this degree 2 of both, or 4 both, right? So the key is same degree. Very good. So same degree, top and denominator. That's type 1. It can be degree 1 over degree 1. It can be degree 2 over degree 2. It can be degree 3 over degree 3. But as long as it's the same degree over the same degree. Okay, perfect. What do you think about the second one? What would you say about the second one? Awesome. That's all I needed. Higher degree in the denominator. That's all I need. That's it. Type 2. And what about the last one? Yes, but we are limited here. Only by 1 unit higher. So for type 3, degree n plus 1 at the top and degree n in the denominator. So mandatory, we cannot go beyond this. We don't have enough information in algebra to go beyond this. We'll have to use the calculator. So type 3 is exactly any degree in the denominator, but the numerator has a degree that is by 1 unit higher. Perfect. Let's start with the first one. Like before with polynomials, I'm going to list all steps that we have to go through. And like with polynomials, the first problem will take us 10 minutes, and the subsequent ones will take us 2 minutes. But the first one is a long explanation. Okay, so for rational functions, a long list, even longer than the one for polynomials. They are more sophisticated functions. What do you think the first one will be? What do you think the first one is? Always. Yes, it's going to be type 1 or 2 or 3. Excellent. Number 2. How do we start for any function? Always. We find the, yes, we will arrange it in descending order if it's not both top and bottom. True. But for any function, we always start with that. Yeah, rational functions will not have degree. Domain. Thank you. Always. Number 2. Oops, I meant number 3. X-intercept, and of course end there what? What can X-intercepts have? Multiplicities. 4. Y-intercept. 5. Vertical. We have never talked about this. Asymptotes. And behavior. Near. VAs. Vertical asymptotes. 5. I'm sorry. I don't know. I'm behind with one number. 6. And behavior. And horizontal or there is no and or slant. A function cannot have horizontal and slant. Asymptote or asymptotes. 7. Symmetry. 8. Max min. TI 84. We can do this by hand. 9. Range. For the first problem, we're going to go through all these. We're going to write all these, but subsequently we will use a table in which we summarize everything so it's clear when we graph it. Ready? So we are going to start with this function that Ryan gave us, x minus 2 over x minus 3. We're going to go over through all these steps and then summarize the information. So f of x equals x minus 2 over x minus 3. Since this is the only one, or the first rational function, obviously it is type 1. We know that. So let's find the domain of this function. And this comes from those rational equations that we looked at a long time ago. So can anyone give us the domain of this function? Awesome. In other words, it cannot be 3. Awesome. Perfect. The x-intercept. How do I determine the x-intercept for any function? No matter what it is. Perfect. Y equals 0, or x minus 2 divided by x minus 3 equals 0 over 1. And that should trigger your memory on something. Because this is a proportion, right? We cross multiply. X minus 2 times 1 must equal? Yes, which is? 0. So x minus 2 equals 0, so x must be 2. So then the x-intercept is? Perfect. The y-intercept. What do I do to find the y-intercept for any function? Very good. X equals 0, so let's find f of 0. What is the top when I plug in 0? Perfect. What is the bottom when I plug in 0? Very good. So the answer is 2/3, and the ordered pair would be?
0.
Very good. The next step we have to discuss in detail, and then we'll continue. So first, let's talk now about vertical asymptotes and behavior of the function near those asymptotes. For this function, what x can you, I cannot plug in. If you ask me, find f of that number, I will have to tell you, sorry. What number? 3. Very good. So most probably, there are situations in that it's not going to be the case, but most probably x equals 3, which is a vertical line, will be a vertical asymptote, VA, of the function. What does that mean? It means that at x equals 3, when we get to graph this function, 1, 2, at 3, we will graph the asymptote, x equals 3. The function does not exist at 3. So what can happen there? Here's what can happen. On this side, the function goes to positive infinity. And on this side goes to positive infinity. That's one case. Then you can go on this side to positive infinity, but to negative infinity on the other side. Or it goes to negative infinity on both sides. Or it goes to negative infinity on this side and positive infinity to the other side. Only because this function is undefined at x equals 3. A rational function will never cross a vertical asymptote because it's undefined. It doesn't exist at that point. So I will come back to my list of things that I have to determine, and I will say x equals 3 is a vertical asymptote for this function. But when it comes to behavior of the function near those asymptotes is exactly what I'm explaining here. It can be, I have to put this down for a moment. It can be, again, positive infinity to positive infinity. It can be negative infinity to negative infinity, or this, or this. How do I check? Here's how I check. And I'll show on the table in a minute. Here's how I check this. I go back to the function, and I plug in a number very close to 3 from the left and from the right. So if this is 3, I'm going to plug in 2.9 on this side and 3.1 on that side. When I plug in 2.9, 2.9 minus 2, what sign do I get? Don't calculate, just give me the sign. Good. When I plug in 2.9 on this side, and then the denominator, 2.9 minus 3, what sign do I get? It's very clear that from the left-hand side of 3, the function goes where? To negative infinity. Because x equals 3 is a vertical asymptote. So so on this side would be negative infinity. Now let's plug in 3.1. 3.1 minus 2. Sign. Good. 3.1 minus 3. So then on this side, on the right-hand side of the vertical asymptote, where will the function go? Exactly. So this is what we call the behavior of the function near the asymptotes, where it's going. If it's going to infinity on both sides, or negative infinity on both sides, or alternate. Okay, so that was, so far we talked about the type, the domain, the X-intercepts. There are no multiplicities in the sense that there is only one solution, multiplicity 1, so there is nothing to discuss. We determine the Y-intercept. We identify the vertical asymptote and behavior near the vertical asymptote. Now let's talk about number 6, which is the end behavior, which we know from polynomials and horizontal or slant asymptotes. Okay, here's what happens with a rational function. There are two possibilities. A rational function can approach a number at infinities. Can approach -5 on this side and -5 on this side. Or, which will be a horizontal asymptote, or it can do this. It can approach negative infinity on this side and positive infinity on this side, or the other way around. But that is not a horizontal asymptote. What type of asymptote is that? It's called slant. So these are the only two possibilities. Type 1 does not have slant. Type 1 only has a horizontal. And the horizontal asymptote is determined from the leading coefficient of the top divided by the leading coefficient of the bottom. So what is the leading coefficient of the top in this problem? 1. What is the leading coefficient? And I'm going to put this in writing for you in a minute. So what is the leading coefficient of the top?
1.
What is the leading coefficient of the top of the bottom? Only for type 1. This is only characteristic to type 1. Leading coefficient of a leading coefficient, which tells us that the end behavior is not infinity or negative infinity, but it's what? 1. 1. So there is a horizontal asymptote. The function may cross the horizontal asymptote, that's allowed. It will never cross a vertical one ever, but it can cross a horizontal asymptote, and in this case, the horizontal asymptote will be 1. And the end behavior will be 1, not infinity. So let me put this in writing. The sun is messing me up a little bit here. So type 1 has a horizontal asymptote which is y equals leading coefficient over leading coefficient. In our case, y equals 1. And that will also be the end behavior. So coming back to our long list, now we know what end behavior is. We know what the horizontal is, asymptote is. Symmetry is not the case here. Max, min, we'll see in a minute, and range we'll see in a minute. So now I would like to summarize all this information in this table so I can graph the function. You told me that the function is undefined at 3. 0 must be in the table. Undefined at 3 means this. This also signifies that there is a potential vertical asymptote in there, but more importantly, the function is undefined at 3. Okay, so this is the domain. Then you said that the function has an x-intercept at 2. Very good. Then you said that when x is 0, y is 2/3. Perfect. Then you said that we agreed that x equals 3 is a VA. We agreed that left and right, negative infinity, positive infinity. We agreed that there is a horizontal asymptote, y equals 1. And there is nothing else. That's all I need. Now let's try to understand all this information and then decide how to graph. Here's what I see. I see that the function is coming from close to 1. It's coming down to 2/3 because this is 0.6. From 1 is coming down to 0.6, down to 0, and it will come down to negative infinity. On the left-hand side of the vertical asymptote, one more time, from 1 down to 2/3, down to 0, down to negative infinity. Let's see on the other side. It's coming from positive infinity, and it will come down slowly and approach 1. That's the graph. So when we graph functions with asymptotes, we must graph the asymptotes first. They are not part of the graph, but they have to be graphed first. So I have to graph y equals 1. Not a solid line, y equals 1, the horizontal asymptote. I have to graph x equals 3. As the vertical asymptote. And now I'm going to plot these points. So 2, 0 is this point. 0, 2/3 is 2/3 here. And now I follow what I see. From 1, under 1, coming to cross the y-axis, coming to cross the x-axis, and on this side it's approaching negative infinity. Ready? I do this with one hand, I'm sorry. It's not going to be perfect. I have to hold my tent here. On the other side, from positive infinity down to 1. And this is the graph of f of x, x minus 2 over x minus 3. Now, if we want to do this, if we want to do this with a graphing calculator, let's do this, please. My apologies, I'm not ready. I forgot to get this started. Please plug in y equals with parentheses around the top and parentheses around the bottom. Otherwise, you will graph something totally different. So in y equals parentheses x minus 2 divided by parentheses x minus 3. Close the parenthesis. And what other function do we have to create as y2 because the calculator will not graph it? What do you think? What is the other function?
Horizontal.
1. Yes. The calculator will not graph it. So we still need to know, okay, I'm going to zoom in and say, okay, I'm going to choose the standard. Here it comes, crossing the y-axis, crossing the x-axis, and here comes the horizontal asymptote. What is missing? The vertical asymptote. I have no idea how to put it in, but most calculators will automatically put it in. I don't know how to put it in the software. But we knew how to graph it from the very beginning. Was this difficult? No. Okay. Can we move on to type 2? Or you would like to see another type 1? Type 2 is even easier than type 1. It's all the same, just one difference.